Okay, so let's get started today. I wanted to point out we have an exam a week from Thursday that's going to cover everything that we have dealt with in databases, including the material from today, plus on Thursday and Tuesday we're going to be talking about NoSQL. So you'll be responsible for that material too, although what we'll be talking, you're only going to be responsible for what I call factual material for NoSQL. We will be going over a NoSQL database called MongoDB. You'll not yet have had an opportunity to do the homework, so I won't expect you to be able to write MongoDB queries, but I will expect you to be able to read them because they're not that hard to read. So I have, if you go to the exams link, you can find a sample past midterm, and you'll see that I ask a lot of multiple choice and multiple answer questions, just like I do for the quizzes. In fact, some of the questions are always drawn from the quizzes, so it's always good to review the quizzes before the exam. On the multiple answer choices, I always give you now the correct number of answers. I didn't in the past, but then I found out people would start like selecting everything, and then it's hard to figure out how to assign credit. So now I tell you how many answers there are, and if you choose more than that, you get points taken off, but if you get some of them wrong, that's okay. So if I were to say here on 15 that there were 3 correct answers, and you got 2 out of your 3 answers correct, you'd get 2/3 of the points. So that's different than Canvas, which deducts points when you have incorrect answers. And then I also have you do some writing of things. I can tell you that in general, the questions that you need to be prepared to actually answer are SQL queries, relational algebra and relational calculus queries. You should be able to draw entity relationship diagrams. You should be able to convert relations to second and third normal forms. And you should be able to do stuff on B+Trees and extendable hash tables, which we will be doing today. So, strongly recommend that you look at the sample midterm and its solutions. Strongly recommend that you review the quizzes and their answers. If you didn't do a quiz, unfortunately, I think Canvas won't show you the quiz, which I think is pretty crummy, but there's no way I know of to make Canvas show you the quiz, so you'd have to try to get the answers from a friend. For the final, someone actually was kind enough at one point to copy down all the quizzes and solutions, which actually, right now is not available because I don't want to give them away yet. But, so go over the quizzes, and basically you're responsible for pretty much all the material that we have covered thus far. I believe that I do have a study guide. Let me check and make sure that that is the case. Yeah, I do have a study guide which I will post, but it basically just goes through everything that we have covered. So I will post that in the next day or so. So it just kind of says what you need to be aware of, and I'll add some stuff for MongoDB to it. And what you should be able to do, so write relational algebra queries, blah, blah, blah. And so it gives you stuff you should cover, and then typically things you should be able to do. So the first part is kind of stuff you should know for the multiple choice and multiple answer. And then I will say, in addition, this kind of stuff here is stuff that you need to be able to do in addition to just the multiple choice and multiple answer. You actually have to be able to demonstrate your knowledge of it on the exam. Okay, so again, I'll have that posted in another day or two. So questions about, you don't need to bring Scantron forms. What I have you do on the exam, it just comes, I print it out, and you circle your answers, and then on the things that require you to do more, you put it into the empty spaces. So all you need to do is bring a pen or pencil. I suggest pencils just so you don't have to scribble out a lot of stuff. It's closed note, closed book. So, questions about it? Okay. So, in that case today, we are finishing up with physical design. And in the videotape lecture, why am I in 140? Here, wait. There we go. There we go. So last time in the videotape lecture, I went over the things like the hardware involved with databases, like disk versus solid state memory, seek times, latency or rotational latency. So stuff you have to be worried about with the hardware. Then we went over indices, how you select indices. Finally started into how you actually organize the files on secondary memory. And there's two primary structures for that, B+Trees and extendable hashing. Each of them an extension of a scheme you should know. B+Trees are an extension of binary search trees. Extendable hashing is an extension of hash tables. And started into B-trees last time. So B-trees are used for physically clustering the data in a database. So we use B+Trees for clustering indices. And remember, there's only one cluster index per relation. And primary key or primary indexes. Remember that it is unusual to index on the primary key because it's, or put a cluster index on a primary key, because what kind of queries do we want to do on a cluster? Range queries. So artificial keys, you basically never want to do a range query on an artificial key. It's useless. So typically the cluster index is on some other attribute like name, or if you had a database of races. I used to be a runner. I used to care about the people around me, so I might ask, give me all runners who ran a 5K between 16 and a half minutes and 17 and a half minutes. That's a range query. So you might, in that case, want the cluster index on the finishing, or the finishing times, how long it took to run the race. So B+Trees are used for clustering indices. Extendable hash tables tend to be used for the secondary indices. Okay, so you tend to use them for the secondary indices because they tend to be faster than B+Trees. Okay, so last time you kind of saw a B+Tree. There were certain properties. So here I have a B+Tree. I'm going to insert 100. And whoops, what happened? Oh, shoot. Reloading is not what I want it to do. Darn it. Insert. Oh, come on. Gotta be careful. Okay. degree 5. Let's do some quick inserts. Speed up that animation. Okay, now let's make this full size. Not sure if I can really, if I can make this, see if I can make it bigger in any way. Nope, the answer would be no. So if you're having trouble reading this, you may have to, let's see if I can, there we go, we can boost it. Okay, so here's an example B plus tree. So we talk about the degree or order of the tree, and the degree is the maximum number of children that an interior node can have. And then we talk also about this factor L, which is the number of records that can fit into the leaf nodes. In a B plus tree, we only store records in leaf nodes. We store keys in the interior nodes. So if a interior node can have 5 children, it can have 5 minus 1 or 4 keys. So if we have a tree of order M, then that means there can be up to M minus 1 keys in an index block. And we also have a minimum number of keys per block. That's M divided by 2. So every interior node must be at least half full. Same thing for the leaf nodes. Every leaf node must be at least half full. And as we showed last time, that means if you do that, then you achieve it means that the tree is no more than M divided. So this is the ceiling function. If you have n records and you have M is the B is the order of the tree, then the depth of the tree, this is the depth. It also gives you the approximate number of disk accesses you need for find, insert, and delete. Will all, on average, require that many disk accesses. And that's what we're trying to minimize, is the number of disk accesses, because as pointed out last time, the operations we perform in memory on those blocks, we can basically perform all the operations we need to perform on a block in the time it takes to do a disk access. Disk accesses are very slow, so the limiting factor in retrieving information from a relation is the number of disk accesses. With the B plus tree, the minimum or the maximum number of accesses is log m divided by 2n. We achieve that by ensuring that every interior node is at least half full. Okay? So, if you want to insert into one of these trees, we'll talk about the find operation is pretty easy. If you're trying to find something in one of these, you start at the root, and as long as your key is less than the key, you keep going through that node. So you do a linear search through the index block. So let's say that I was trying to find 80. So I would find that 80 is not less than 60, so I would go to the next key, which is 90. Find 80 is less than 90, so I would drop down. I would follow that pointer to the child. And this is a leaf, so now I'd simply do a linear search through the leaf, and I would find the record with 80. Okay? So in the rule is that the left-hand pointer points to a left child with entries less than you. Your right-hand pointer points to entries that are equal to or greater than your value. So here you see 90 is the first record in the right child. Here you see that 60 is the first record in the right child for 60. So find, pretty easy. Okay, insert is pretty easy if there's room in the leaf node for the record. So here we're also assuming L is equal to 5. So this visualization, which was written at, I think it's UC, I was going to say UC Fresno. I think it's Fresno University. The person who wrote it assumed that the number of records in a bucket is the same as the degree of the tree. That would normally not be the case. They're normally different. I'll give you a formula for computing those two numbers, but first let's just see how you do inserts. So let's say I want to insert 200. Well, 200 you can see is not less than 60 and not less than 90, so it's going to go into this right child. And you can see there's enough room in the bucket. It can accommodate up to 5 entries. So when we insert it, let's make the animation be a little slower. Okay, so we're going to insert 200. And you can see it comes down to this one. And it's going to put 200 right in there. Okay, we're going to now insert 250. Same thing, it's going to go into this bucket. It's going to be big enough to absorb it. Whoops. Okay, it's assuming in this case that, it's assuming that the number of elements that can be stored in the leaf is only 4. Okay, I was wrong. So it's assuming in this case that L is equal to M minus 1. So it's assuming 4 items can be stored. So I'm going to insert 250, which is going to overflow the bucket. It should go in here. When the bucket splits, I want you to move the odd number. In this case, there's going to be 5 elements in this bucket. That's too big. So I want you in this course to move the extra tuple to the left-hand side. This visualization moves it to the right-hand side. Why do I do that? So you can't use this visualization to answer your homework questions. Okay, that would make it too easy. So right now, when it does the insertion, it's going to actually put the extra tuple on the right-hand side. So if it puts the extra tuple on the right-hand side, that means 90 and 100 will go into its own bucket, and 150, 200, and 250 will go into the own bucket. We also not promote, but copy the first key in the rightmost bucket up. So 150 is going to end up being added here because it will be the smallest key in the rightmost bucket. So doing all that, it inserts 250, and now 150 is going to promote. You see 150 getting promoted. When we're done, we have 2 new leaf buckets. 150 was added here, and you can see it points to the first entry in the new bucket. Yes?
And you're saying, I'm confused on how it differs going left. What do you mean by that in the homework?
So there were 5, okay, let me skip back. There were 4 entries here, right? When I delete 250, there's 5 entries that should go in this bucket. So that means I have to split them. One of them is going to have 2 entries and one of them is going to have 3. Okay? So the way this visualization does it, it always puts the extra tuple in the rightmost child. I'm saying for the homework and on the test, you have to put the extra tuple in the left child. So if this were the homework, 150 would have ended up in the left bucket, 200 would have been the entry up here now because 200 would be the smallest element in the right child. Yes.
Doesn't that change the rule, though, that you're saying that in the right side, the right key is going to have equal or greater size? Because right there, it's going to be in the left key of 150, it's equal or greater size.
So what I'm saying is 200 would then be the...
Oh, so you're putting 200 up there.
Yeah, so I'm saying in the homework assignment, 150 would end up over in this left bucket, and 200 would end up here. Okay?
Is that in the write-up for the homework?
Yes.
Okay.
But I'm also saying it here.
I mean, yes, I was just...
Yeah. Actually, if it's not, I'll make sure it is. I have to check that.
Thank you.
You're welcome. What was the other thing I wanted to say? You'll notice it's duplicated because here, this is the record down here. The whole record is here. They're just only showing the key. Up in the interior node, it's only the key that is kept, not the whole record. Okay, so now I will keep going. I'm going to insert 30. It will be big, and this one will be big enough to accommodate it. Now I will insert 50. Again, 50 is going to go into this bucket because it's less than 60. Now I'm going to put in 25. That's going to split this, actually just for grins, I'm going to put 45 in. No, I'm going to put 35 in. So 35 is going to go right here. It's going to split the bucket. 35, 40, and 50 will go into one bucket. 20 and 30 will go into the other bucket. And what's going to get up here in that case? 35 will go up because it will be the smallest value in the right bucket. Okay. By the way, if you do this animation, you can control the animation speed here, and if you're fast enough, you can hit pause, which, because I don't have the controls showing, I can't do that. Otherwise, I would try to pause it for you, but you can do it on your own. Okay, now we're going to force this root node to split. So we're going to add some entries. We'll do it down here, let's see, between 35 and 60. Let's add 55. Whoops, I don't want to delete 55. I want to insert 55. It's going to be big enough. Okay, now for the interesting case. I am going to insert 45. Okay, 45 is going to be between, it's not less than 35, it's less than 60, so it will go in here. That's going to cause this leaf to split. 45 will go in with 50 and 55, so 45 will get promoted. The problem is I can't put 45 in here because that's too many keys. So we're going to have to split this block. So it would be 35, 40, 60, 90, and 150. In this case, because it will be an odd number, we will promote the middle element, which will be 60, because that will be the middle element. 60 will go up into a new root node. 35 and 45 will go into their own node, and 90 and 150 will go into their own node. 35 and 45 will, 35 and 45 will point, well, let's go a little more slowly. So I'm going to make this smaller for a moment. Wait a minute, why isn't this getting smaller? Now let's try something else. Let's make the height 250. We're almost, let's make it 200. There we go. Okay, so I'm going to insert 45. Let's make this bigger. Okay, so 45 is going to be put here. There we go. So we paused it. 45 is there. Now I'm going to step forward. So 45 came up to here. But this is too big now. But notice we have 6 children. So what's going to happen, 60 is going to get promoted. 30 and 45 are going to go off into their own block and will handle these 3 children right here. 90 and 150 will go off into their own block and handle these 3 children. So if I step forward, 60 is going to get promoted into the root. 35 and 45 went off into their own. 90 and 150 went off on their own. Yes?
So in the homework version, 45 would be in that 35, 40 block and 50 would have moved up?
Correct. That is correct. Now notice the root is the one exception to our rule. The root does not have to be half full. So the one exception to our rule that all interior nodes must have greater than or equal to m divided by 2 children is the root. The root is allowed to be less than half full. Okay, and so this was easy because it was an odd number of keys in the block. If you end up with an even number of keys and need to promote, I want you to promote the leftmost one. So if I had a max degree of 4, then skipping back here, let's say that I had a max degree of 4 and I was needing to split this node. So there's 2 middle keys, right? I want you to promote the leftmost one on the homework or on the exam, so 60 would promote. Okay, so questions about, so I'm going to reinsert 45. Step forward, step forward, step forward. So hitting the pause button is really nice because notice it also has a little bit of explanation along the way about what's going on. Splitting. There you go. Okay, you can also step back. So it's really nice with the animation if you play with it. If you're having a little trouble seeing what I'm saying, you should be able to play with it, get it to work. Okay. Hopefully you can see that because we only split when a leaf node gets full, that guarantees that the 2 split nodes both have at least L divided by 2 records. When we split a interior node, we only split when we exceed M. So again, it's M plus 1. So when we split it, each of the 2 split nodes has M plus 1 divided by 2 keys, which again assures we're greater than M divided by 2. So this is basically like a binary search tree with higher numbers of children. So questions about insertion? Yes?
So you may have said this and I missed it, but the 2 middle nodes hold keys for the leaf nodes, right?
Right.
How come it doesn't hold the key for the leftmost?
Because it's just like, think back to a binary search tree. Okay, so if you have a binary search tree, binary search tree also never has it. If it was a copy, it wouldn't have 2. It only has 1. It has 1 less than the number of things it points to. So here, the leftmost child, it doesn't have anything for the leftmost child because it's just all keys less than 35 go here. All keys between 35 and 45 go here. All keys greater than 45 go here. Now there's an implicit thing that is all keys between 45 and 60. Does that make sense or not?
Yeah.
Okay. Other questions? Okay, it gets more fun with deletion. So when we delete, we have to be careful. Well, let's actually add another key. So I'm going to add, let's see, 52, just so I can delete it without having any issues. Okay, so if I need to delete a key, the easy case is when I delete a key from a bucket, and when I'm done, the bucket still has at least m divided or L divided by 2 records. So in this case, it can hold up to 4 records, so L divided by 2 is 2. So if I delete something and there's still at least 2 records, I'm okay. So I'm going to delete 52. Okay, hit pause. So it finds where the node is, and because 52 can be deleted without making it smaller, it does it. Okay, we good? Okay, actually now, let's do another case, but I'm going to add in 52 again. And I'm going to step up the animation speed because I want this to go fast for a moment. I'm going to split that puppy again with 47. Okay. So now I'm going to delete 47. Okay, when I delete 47, it makes this leaf bucket be too small. Okay, it would now have fewer than the minimum number. So we'll start it and we'll pause. Okay, so I'm going to step forward, going to step back and explain what's going to happen. The first thing what we want to do is, if possible, we look left and right to see if we can borrow a key from or a record from a neighbor to bring us back up to the minimum. If we look left, we cannot borrow from that neighbor because it would make that neighbor be too small. But if we look to the right, if we borrow 50, the smallest key from our neighbor, that neighbor will still meet the minimum number. So we can take it from our right neighbor. So what we're going to do is delete 47 from here and move the record with 50 over to here. When we move the record from 50 over to here, we have to adjust this entry because now the smallest entry in this bucket becomes 52. Okay, so watch all of this go. 50 moved over. Now 52 is the smallest, so we adjusted that. Okay? We see that? Okay. Now I'm going to insert 70. Okay, and now I am going to delete 55. Now, you would think, okay, I can't borrow from my left leaf because it's too small. And you might think, oh, I can borrow from my right neighbor because it has enough. This doesn't work. Does anyone know why I'm not allowed to borrow from this node, even though it looks like a right neighbor? They don't have a common parent. You're only allowed to borrow from siblings. So don't get suckered by the fact that this visualization is using arrows between the bottom leaf nodes. Because the block containing 60 or the leaf containing 60 is not a sibling. It doesn't share a parent with the block containing 52. I can't borrow 60 and move it over here. I can only borrow from my left or right siblings. Here, there is no right sibling. Don't get suckered, okay? So it turns out that I can't borrow from anyone. When I can't borrow from anyone, I have to merge with another leaf node. So in this case, I'm going to merge with my left sibling. Okay, if I can't borrow, I merge with my left sibling. What's the one obvious exception? If it's the leftmost sibling, it has to merge with its right sibling. So if I was deleting 20, it would have to merge with its right sibling. But otherwise, we merge with our left sibling. So what's going to happen is 55 is going to get deleted, and we are going to merge these two blocks. Okay, so 55 has been deleted. Now we're going to merge these two blocks. Okay, and a lot went on, so I'm going to step back. When I merged these two blocks, this block disappeared, so 52 disappears from up here. So when we're done, we only have 35 and 45 up here. Okay, stepping back. See, we merged these two blocks. That's going to remove an entry from the parent. Okay, the rightmost, the key associated with the right block will go away. Does that make sense? You think you know how to do it? Good. Why don't you try to delete 90? So think about maybe take a piece of scrap paper and see if you can figure out what happens if I delete 90. Okay, do we have an answer? Someone want to help me out? What's going to happen when I delete 90? That's right. So I'm going to take a record from my left sibling because it's big enough to afford the loss. So 80 is going to slide over. And because 80 becomes the smallest key in this leaf, 80 is going to appear up here. Pardon?
Unless you're doing the homework.
No, if you're doing the homework, you borrow from the left.
You just create a new node to the left if you're inserting.
I'm sorry, I'm deleting.
Well, but I mean, like, when inserting is when it's to the left.
Yes, right. But on the homework, you look left. So we come down here, just like here, we look left. We're going to switch. Oh man, I deleted 80. That's not what I wanted. Skip back. Meant to delete 90. Okay, step forward. 90 deletes 90. Now it's going to borrow 80, and 80 came up here. Okay? Now, to get interesting again, we are going to delete, and that's not going to be interesting. Deleting 40, still, let's see. What's going to make it interesting? Deleting 70. Okay. We are going to delete 70 next. Okay. When I delete 70, I can't borrow from the left because I have no left sibling, and I can't borrow from the right. So I'm going to have to merge these two blocks, right? So let's go and start doing that. So I delete 70. I'm going to have to merge these two nodes. Okay, so I merged these two nodes, and what key is going to disappear from here? 80. Very good. Now there's a problem. What's the problem? This node's no longer big enough. It has to have a minimum of m divided by 2 keys, and it doesn't. So it does the same thing. It's going to try, if it can, to adopt something from over here. But there's nothing to be adopted because this is already a minimum. So I'm going to have to merge. Okay? So when I merge these two together, 60 needs to drop down because, step back, when I merge these two, there's no need for this root node anymore, right? Because these two become the new root node. So that's what's happening. 60 slides down and becomes part of this new configuration. So we lost a level. Okay? Now I'm going to, does everyone see what happened? It's always fun to do on a homework assignment because deleting a root is an unusual case that you should be familiar with. So y'all familiar with it? Okay, now I'm going to add a bunch of keys really quickly to get to one more situation. So move that animation speed up to full on. Let's see, insert 70. Don't worry about what I'm doing. I'm trying to get to a tree that I want. And it's going to take me a few moments to get there. Okay. Now I am where I want to be. So I want to illustrate the merge case up here so you can see what's going on. So let's say I delete 15. That's not going to work. Let's say I delete 5. Okay, so I delete 5. Too fast. Got to slow down the animation again. Okay, delete 5, pause. Skip. No! Skip back. Delete 5. Step forward. Okay, we're down here. We try to delete 5, and what do we have to do? Merge. Because we can't borrow from our right sibling, so we're going to merge. So 5 disappeared. We're going to merge. When we merge, what's going to get lost from up here? 10. Okay? But now it's too small. Still not what I want. Sorry. More inserts required. Got to get bigger. Okay, just a sec. Let's see. 57. I want to get to where I can actually increase the animation speed, where I can borrow something. There we go. Okay, now I'm going to delete 5. Move the animation speed down. Delete 5. No! Oh, it just killed the entire tree. Oh, it didn't. Thank God. Okay. Thought all that work to waste it. Okay. I was going to have to recreate that entire tree. Okay. So, how do I force 5 back onto the screen? I can't. Well, that's too bad. Oh, how do I? Okay, the problem is 0 and 5 are off screen right now. Try full screen, that's a good idea. And it's still not working. Okay, so what's going to happen is we're going to merge, 10's going to disappear. Step back. Okay, so when 10 disappears, this thing is too small, right? It has only 20. But now it can borrow a child from here. So what it's going to do is it's going to borrow this child, which is 35. It looks like 45 is what you should move over here, right? Because this is the key. You think, oh, I'll just move 45 over here. But that's not the child you're getting. The child you're going to borrow is this child right here with 35 and 40, right? So what's actually getting moved is 35 is going to come over here. 45 is going to go up into there. I believe is what's going to happen. Yes. Okay, because I now am pointing to 35, and this entry is now pointing to this block, and this block. See, this entry now points here, here, and here, so its smallest value is 50, and 45 ended up going up. So you have to be a little careful. The merge process isn't quite the same as is with a leaf, right? So again, deleting 5. I delete 5, so I have to merge the bucket. When I merge the bucket, 20 disappears. I adopt this child right here, so 35 comes down, 45 moves up. You may have to work that out on your own. I'm not claiming that one's easy. I think that's the hardest case. And the reason it's the hardest case is because you think that you should be able to move 45 over here and you can't. Notice what would happen if you move someone tell me what the problem is if you move 45 over here. What's being violated? 45 is not less than 35, is it? That would be the problem. You can't just move 45 over here because it wouldn't be less than 35. So your tree would be all messed up. So what you need to do is look at the child that you are getting. When you merge with this bucket right here, you are getting this leftmost child. So you are getting 35. And then the leftmost key here is going up and replacing 35. Okay? I'm going to move on because I have to. I need to get to extendable hashing. But this visualization is very good. Okay? Now, the last thing, I got a good question, and that is how do I calculate L and how do I calculate M? And I try to make M and L as big as possible because the bigger I make M, the bigger this it makes this logarithm smaller, right? So I make M as big as I can. So in general, if my block size, let's say my block size is B equals block size. So that's my block size. And P equals my pointer size to my child. So that's the disk address that we point to. That's how much a disk address costs. And K equals the key size. Then M is going to be equal to B divided by roughly P plus K. It's actually, you're going to have, that's roughly right. You have, though, you only have M keys, but you have M plus 1 pointers. At any rate, it's roughly this. So I'll just put roughly that. That gives you the maximum possible size of M. You may have to make M be 1 less because, as I said, there are M plus 1 pointers. But I don't want to make it too complicated. And L is equal to B divided by the size of a record. And of course you have to take the lower bound on that. And you have to take the lower bound here. So if you don't know what, this stands for lower bound. So L is equal to the block size divided by the record size. M is equal to the block size divided by the sum of the pointer and the key. Because each entry in the interior node is essentially a pointer and a key. So you make L and M as big as you can. Questions about that? We good? Okay. So take a deep breath. We're moving on to a different one, which is an extendable hash table. So let me, for that, I don't have a good visualization for it. So I'm going to have to bring up the handout I have for it. Not there. Probably in notes. Or is it going to be in slides? Ah, there we go, extendable hashing. Okay. So, here's the idea behind extendable hashing. You have, with extendable hashing, you're trying to hold the number of disk accesses to 2, actually 3. Basically, you want your index to be no more than 2 levels high. So this would be your index, and then these things would point to the actual records. So what's not shown here is pointers to the actual records. They would be down here, so you'd actually have a 3-level index. So The idea with extendable hashing is you always have no more than 3 disk accesses, no matter how big the relation gets. So what you're going to do is each key is going to be hashed into a 32-bit number. So you have a hash function, you apply it to the key, you get a 32-bit hash, or you get a 32-bit number. What you're going to do is you're going to organize your entries by the leading bits. So here we have 4 entries in our top level index. So all keys whose first 2 bits are 0, 0 will end up in the leftmost bucket. All keys whose leading 2 hash bits are 0, 1 end up in the second hash bucket. All keys that have the leading 2 be 1, 0 end up in the third hash bucket, and so on. Okay? And then these in turn point to the actual records. Remember, this is a secondary index now. We don't use extendable hashing for clustering. We use them for secondary indices. So each one would now point off to some record. So it requires 3 disk accesses at most to get it. Oftentimes this top level index will be cached. So in main memory. So oftentimes you'll only have to go out here. Okay, this is treated as an array. You might think, how in the world, if this top level thing is on disk, how can I avoid doing a linear search through this thing? The answer is easy, because this is like an array, right? It goes from 0 to 3. So if you know the number of entries that you can put in a block, let's say I could only put 2 entries in a block, so this requires 2 blocks, then I can easily calculate which block it's in, as long as they're all contiguous, by just dividing the index by the block size. So if I have to go to 1, 1, that's 3 divided by 2, it goes to block 1. As long as all the blocks in the main index are contiguous, we can immediately jump to the right block. So the idea is the top level is like an array, and we can immediately jump to the appropriate block in that array. Okay? Now, what happens when we overflow a block? So right now, we're assuming we can get 4 entries per block. Okay, so what we're going to do is we are going to insert this key right here, 100,100. So if we want to insert 100,100, 10 is its 2 leading bits, so it should go into this bucket. This bucket is full, so we must split the bucket. What do you think is the most logical way to split the bucket? We'll consider 3 bits rather than 2 bits. So we'll move all bits that start with 100 to one bucket, and all bits that start with 101 to the other bucket. So when we have to split a bucket, we do it by considering 1 more bit. Well, that's a problem because this main index is only using 2 bits. So when we split it, we have to double the size of the index so that the main top level index now uses 3 bits. Now the only bucket we need to split is this one right here. All the entries with 100 go into one. All entries with 101 go into the other. So we did that. We were adding 100, 100, so it went into this bucket. All the 101s went into this bucket, so these two buckets are now using 3 bits. But the other 3 buckets are still only using 2 bits. So if you'll notice, we keep track in each bucket of how many bits it's currently using, how many leading bits. And you'll notice when we doubled the size of the top level index, in the top level index, 2 entries now point to the first bucket, 2 entries point to the second bucket, and 2 entries point to the last bucket. And that's because we didn't split 3 of the buckets. So 3 of the buckets still only use the leading 2 bits. Therefore, both in the first bucket, both 0, 0, 0 and 0, 0, 1 point to the first bucket because it contains all entries that start with both 0, 0, 0 and 0, 0, 1. Okay, so what happens if we now add an entry to this bucket? Okay, so we are going to insert 0, 0, 0, 0, 0, 0. So when we insert 0, 0, 0, that matches this entry. We go to here, too big. So now we're going to have to use 3 bits. So all 0, 0, 0s go into one bucket. All 0, 0, 1s go into the other bucket. But we don't have to split the top level index anymore because it can accommodate it. When we do the split, all the 0, 0, 0s have gone into this bucket. All the 0, 0, 1s are in this bucket. But now instead of 0, 0, 0 and 0, 0, 1 going to the same bucket, they point to 2 different buckets. And we updated the number of bits, leading bits that these 2 buckets use from 2 to 3. It's a very simple idea. It was discovered in the 1980s, and almost all of the work was required in mathematically analyzing it. The idea itself of splitting this thing is pretty simple. There's only a couple caveats. One is it can happen, it's very rare, but it could happen that when you do a split, everything goes into one bucket, right? If it's possible, but very unlikely, that all of these would start with 0, 0, 0, in which case going to 3 bits wouldn't help you. So then you'd have to split it. That doesn't work, so you'd have to split again to go to 4 bits. Don't worry about that in the homework, but that's something you'd have to worry about in practice. In practice, these buckets are enormous. They contain something like 1,000 entries, maybe 500. The chances that all 500 entries would have the same leading 3 bits is vanishingly small. But it could happen. Okay, the other problem is that you could have so many duplicates. So 2 keys could hash to the same hash value, right? That's the other incredibly unlikely scenario. If your hash function stinks and it hashes too many keys to the same hash value, that might be a problem because let's say you could only store 500 entries in a bucket, and let's say it tried to hash 600 keys to the same bucket, 600 keys to the exact same hash value. There's no way you can store 600 keys with the same value in the same bucket because no matter how many times you split, they have the same leading bits. So your hash function better be good. It can't hash to the same hash value all the time. Okay, again, in practice, this never comes up, but those are the 2 things you have to be careful about with extendable hashing. You may have to split more than once if adding an extra bit is not enough to, if adding one bit, if all the entries still are in common, you'll have to add a fourth bit. The other problem is if the hash function is no good and it hashes all the keys to the same value. Okay, so the big question, so if you're starting from scratch, I didn't show you how to start from scratch, but that's not very hard. So if you're starting from scratch, let's say that I'm just going to use 4-bit entries to start with. So let's say this is my initial insertion. So initially, if you can fit 4 into a bucket, that's good enough. It's only, and now you're using 0 bits to distinguish them. You don't even need, in effect, a root. The root is one thing. Now we try to add 1, 0, 0, 1. Now we have to split, so we're going to use the first bit to do the split. So all the zeros will move to one bucket. And all the ones, leading ones, will move to the other bucket. And now we would have a 2-entry thing, 0 and 1. Each of these is using 1 bit. And that is how you start. Got it? Okay. So the big issue early on, they implemented it, and everyone was worried about, what do you think the potential problem is here with keeping it at, with what happens when you're always splitting the top thing? What could potentially happen? What happened, remember the thing where the king, I think, taught the story of the king hired someone to teach his prince chess, and the king was really happy with the outcome. And the king said, how much do you want to be paid? And the instructor deviously said, I'm a man of simple means. How about for each square of the chessboard, you start by putting 1 grain of wheat on the first square, 2 on the second, and you keep doubling it each time. And the king was overjoyed. What a cheapskate. I mean, it'd be easy to pay this guy. The guy wants nothing. So he agrees to the instructor's deal. And what happened? The king was bankrupt. And why is that? Someone tell me. Why did the king go bankrupt? Exponential growth. So 2 to the 64, there's not even, I think, that many atoms in the, well, there may be that many atoms, there's that many atoms in the universe, I think. But just suffice to say, 2 to the 64 is an enormously big number. So 2 to the third doesn't look bad, but that's not a whole lot of records. Everyone wanted to know what happens because you're doubling the size of this top-level directory every time. That's the key to making this thing work, is doubling the size of that top-level directory so that it acts like an array. So after about 20 divisions, this thing is enormous. So the question is, how big does it get in practice? Well, in practice, they found it didn't get very big. Okay? And what they actually discovered with a lot of math is that in general, where do they have the number? Right here. So in general, the expected number of entries, whoops, I can't make it, but this is the number right here. The size of the top level directory is of this order, n to the 1 plus 1 divided by m divided by m. Okay, so it's essentially n divided by m. The only thing with the exponent is this m. It does grow a bit exponentially with this exponent. How big is m in general? About 500, because you can normally fit about 500. Unix blocks are about 4,000 bytes. Keys are integers, which are 32 bits. Disk addresses are either 32 or 64-bit addresses. If they're 32 bits, then that's essentially 8 bytes per entry. 4 bits for the key, 4 bits for the disk address. You can get roughly in a 4,000 byte block, 500 entries. So this is roughly n to the 1 plus 1 divided by 500. That doesn't grow very fast. This was a very pleasant surprise. The top level directory just doesn't grow that quickly, it turned out. Don't worry about the math, it is very involved. Okay? Almost all the work in the initial paper, as I understand it, went into the mathematical analysis. Okay, if you look at the expected number of leafs, okay, this is the leaf, so this is the directory. These are the leaves right here. The expected number of them is n divided by m log 2 of e, which is natural log of 2. So that is pretty small. Okay, that grows as a factor of the log. And the average leaf is about 70% full, which turns out to be the same as for B+Trees. So for B+Trees, the expected number of leaves is also this number, and the expected occupancy is also 0.69. If you're wondering why these two miraculously come out the same, it's because a hash table is essentially a tree, and it's splitting every time the leaf overflows. The only difference is that in a B+ tree, it always divides exactly in half, whereas a hash table doesn't divide exactly in half because it divides based on this leading number of bits, and sometimes there's going to be more 000s than 001s, right? So the hash tables don't always split evenly the way B+ trees do. So, last question, I'll let you go. Why, given that hash tables don't always split evenly and B+ trees do, why aren't hash tables a little bit bigger? Meaning, if they don't split evenly, which is optimal, hash tables should be a little bit bigger. Why aren't they in general? Not claiming it's easy to see, but it's intuitive when I explain it to you. So as n approaches infinity for the size of the bucket, how do you expect the entries to get distributed? For if the hash function is really good, as the number of records in the bucket approaches infinity. Just think of the number of leading zeros and the number of leading ones. How many zeros and how many ones will there be out of n records as n approaches infinity? If the hash function's really good. n over 2. Very good. So the thing is, if you only have like 20, let's think of flipping a coin, okay? Let's go to flipping a coin. If you flip a coin 10 times, there's a good chance it's going to be in balance between heads and tails, right? There's a good chance there'll be 8 heads and 2 tails. If you flip a coin 1,000,000 times, do you really think there's only going to be 250,000 heads and 750,000 tails? No. So the thing is, the reason that they're almost identical is because the blocks are pretty big, usually around 500 records. Okay? You flip a coin 500 times, it's going to be very uncommon for there to be a big disparity between the number of heads and the number of tails, right? So that's what happens with hash tables. Yes, if M were small, around 5 or 10, you would expect unevenness to make hash tables to have many more leaves than B+Trees. But because M is big, 500 is starting to approach infinity, you expect the zeros and the ones to be roughly evenly distributed. Therefore, most of the time, when you split a hash table leaf, roughly half the entries go to each of the 2 leaves. That's why, in practice, hash tables and B+Trees have the same number of leaves. Okay? It's only if M were really small that there would be a difference, and M is not really small in the real world. Okay? You're good to go. You're ready to do homework 5. Starting on Thursday, we'll talk about NoSQL.